Good morning. Today is the last lecture, and I will explain well the experiments that we did last time and many other things. First, I will recall some of the things that I said last time. Remember that to a partition, lambda, which I, as always, write as in the Russian way, we have the x and y's. Which interlace. What? Thank you very much. Etc. I introduced the transition measure of the diagram. Let me call it mu lambda. And mu lambda is characterized by its Stieltjes transform. Which is just the quotient of the polynomial, which has roots at x and roots at y. Since we have this is a probability measure, and since we have a probability measure associated to a diagram, we can also associate to this probability measure its moments and its free cumulants. And I denoted by Rk of lambda the free cumulants of the diagrams. We can also scale the diagrams, and actually we can define free cumulants associated to any curve, which is not too bad. That is any curve which satisfies omega of x is modulus of x for x large enough, and omega is Lipschitz. Just by scaling this, in this formula, the x and y are integers, but if you scale them by some factor, by the same factor, then you get another probability measure. Just the probability measure scaled by the same factor. And now you can approximate any function satisfying these conditions by some diagram, and the formula goes on. So we get, in this way, a correspondence between probability measure on the real line, with compact support in this case, and Lipschitz function satisfying this condition. The free cumulant satisfies the fact that R1 is always 0, and R2 is just the surface that is the integral of which is of the function which is below the diagram and above the absolute value function. And what I claimed last time, and that almost proved, or I gave you a rough idea of the proof, was that there is an asymptotic expansion of the, well, actually we get the first term in the asymptotic expansion of the characters of the symmetry groups These are the normalized characters. And here sigma is some permutation which can be written as a product of disjoint cycles, non-trivial cycles of lengths L1, L2, Lk. Then this is equal. In order to state this, I just introduce the rescaled partition. By this, I mean just look at the partition as a function and scale the diagram by a factor square root of lambda, so that the surface, this surface here, if you want the second cumulant, is equal to 1. I call it omega. Then there is a product of all cycles. Of some numbers. This is of order 1 as the length, as the lambda goes to infinity. Then sorry, I assume also that the diagram is in some sense bounded, in the sense that the length of the longest row and the longest column are of order square root of n. I assume this. And then there is some there is this, so the order of decay of the characters is given by the size of the group, the n. It is Sn. It's n to the minus the half length of the permutation. Recall that here the length of the permutation is just the sum of Li minus 1. The length of a cycle of order k is k minus 1. So because you need just k minus 1 transposition to write it as a product of transposition. There is this number which gives us which will be some bounded number as lambda grows. And then we have this rate of decay of the character. And then we have some rest, which is smaller. Therefore, we can give a good approximation of the character for some classes of large diagrams, the one which satisfy this. And of course, if you change the A here, you will change the constants which are here in the big O. This big O is uniform once A is fixed, uniform over all diagrams, once you have fixed the A. And once also you have fixed the length of the permutations. And this big O depends both on the length of the permutation and on the factor that A that you put here. Well, it turns out that there is some much more general formula than that. This is an asymptotic expansion, which is very good for making asymptotic analysis of the symmetry group. But actually, there is an exact formula which is behind this. And I want to now tell some things about that. Remember that I introduced a matrix gamma last time. This matrix is a matrix made of elements in the group algebra of the symmetry groups. It is a n plus 1 by n plus 1 matrix. On the first row, you get 0 and 1s. 1s are just the identity in the group algebra. In the first column, you get 0 and 1s. And then on the diagonal, you have zeros. And then you put on the, say this is the 0th column and the 0th row, and then 1 n. And at ij, you put, if I different from j, you put the permutation, the transposition ij. It is a matrix whose elements, entries are just permutation, either the identity or some transposition. It is a very natural matrix, and of course, the group Sn acts by permuting these columns and rows in a covariant way, as you can see. Well, we have this matrix, and I introduced the moments of the matrix in the sense that I introduced the mk, which are 1 over n plus 1 times the trace of gamma to the k. So this is an element in the group algebra. In order to compute it, you just expand this matrix, take the product of the matrix by itself, k times, and then you take the trace, and it is some element in the group algebra of Sn. And it is not very difficult to see that it actually belongs to the center of the group algebra. So this form a family of elements in the center of the group algebra, and actually they form the group algebra is this group algebra is an algebra. It is a commutative algebra. If you take the center, you get a commutative algebra. And what I claim is that they form a multiplicative basis, or not really a basis, but more precisely a multiplicative generating subset. By this, I mean that any element in the group algebra of the symmetric group can be written as a polynomial in the MK. What? In the center. Yes, of. It's not obvious, but actually there is an explicit formula. There is another natural multiplicative generating set, which is the set of conjugacy classes of cycles. If I take cycles, say I will call these elements sigma k. Sigma k will be the sum of all cycles of size k. Well, some of them get repeated because you have if you sum over all the things. So this is just k times the sum of the cycles of length k in the group algebra. Because of course you can, and of course I assume here that the i's are ik are disjoint. Of course, it is defined only if n is large enough. Using this, it is not difficult to see that you can generate the center of the group algebras. Every element can be expanded in a polynomial in these elements in the group algebra. There are relations between them when n is finite, of course, but when n goes to infinity.
I'm sorry, I1, ik is a cycle?
Yes, yes, it is the cyclic permutation I1, ik. I1 goes to I2. They are just different. I don't say they are not ordered, sorry. They are just between one and, they are not ordered, of course. Just take any set of k elements in one n. Pairwise disjoint. Any set of k elements, if you want. Any subset of k elements, and ordered in some way, and it gives you a permutation. And you see, you get each cycle exactly k times because you have this invariant by cyclic permutation. I didn't say that? No, but I say it today. So we have here two multiplicative generating sets. And actually, I introduce a third one, which are the RK. RK are the free cumulants of the MK. From this formula, you see that the MK are some kind of moments. There are the moments of the matrix gamma. No. What I claim, there is a formula which is there is an explicit formula for expressing free cumulants in terms of moments, in terms of cumulants. This formula, I said, can be inverted. There are polynomials. No, I mean, this is just, there is a polynomial relation between the Mn and the Rn, and it can hold in any commutative algebra that you want. It's just a relation between, for example, you have M2 is R2 plus R1 squared. Here is an example.
But R2 is equal to Mn has a meaning.
Yes, but I mean, if M has a meaning, then I can define the R by this formula. Okay. What I claim is that, say, R2 is M2 minus M1 squared. So in my case here, M1 is 0, but and say R3 is N3 minus, and there are some formulas.
Since you already defined R's,
if you want, it's just, you have two sets of variables which are related by some polynomial formulas, which are invertible. It's a triangular system because in each thing so this is Rn plus a polynomial in the Ri. This can always be written in this way, and so this system can be inverted, and I can express the Rn's in terms of the M by some polynomial formula, universal. I mean, last time I also showed that there is some. If you look at the generating function of the M's, the sigma of the Zn, Mn, and the generating function of the R, there is some, I don't remember exactly the
can you not call them Rn?
why?
Because they are numbers defined there.
They will be the same. No, this depends on lambda. This depends on lambda. And I will explain the connection between the two. The connection is very simple. Okay. I define the Mn like that. Well, last time also I said that actually if you evaluate the character chi lambda on Mn, well, this is exactly the integral of x to the n d mu lambda of x, where mu lambda is a transition measure. So the Mn's are moments of this matrix. They are in some algebra. If you evaluate them in some representation, you get this formula. So they are actually moments of some measure when you evaluate them. When you have not evaluated, I said they are in the center of the group algebra. When I evaluate them in some representation, they are given by a constant. And what I claim is that this constant is this number. And this is due to the fact that gamma, in some sense, is a Cauchy-Murphy element of order n+1 in some basis. It's another way of writing down the Cauchy-Murphy element of degree n+1, gn+1. And the transition measure can be also defined as a distribution of the Cauchy-Murphy element of order n+1. Oh, yeah. So, yes, it's not the same n, sorry. Yeah, you're right. With? I mean, this is valid for any k, actually. This is valid for any k, yes. Yes. If I have lambda, if I have a partition, I can associate to it a transition measure. this transmission measure. So if I have lambda, I have fixed some n, of course, which is the size of the partition. And then I'm looking at representation of Sn. What I claim is that so this element, actually, this element is in the center of the group algebra. So it has some, it is a multiple of the identity when I evaluate it in some representation. And this multiple is just this number, which is here. And then, of course, if I evaluate these elements, which are elements in the center of the group algebra, in the representation lambda, then they become these numbers, which are here. Okay? So you see we have some elements in the group algebra which in some sense contain all these numbers for all the representations of our group. But they are in some sense above. We can obtain all these numbers just by evaluating these operators in some representation.
Why is it of course at this point?
What? Why is it? Well, if you believe in this, then this is true, clearly, because why you should believe in that? This is what I said last time, and I mean, you have to do the computation. Maybe I can. As I said, this is just the fact that this, if I evaluate gamma, in some representation, which means that I evaluate all these elements in the group algebra in some representation of Sn. So this belongs to it is an element in this space, and I can identify this space with the space of the induced representation of V lambda from Sn to Sn plus 1. There is a way to do that, so that this element becomes Gn plus 1. This is a claim, and this is a computation that you have to do. This is a claim. Because well, it becomes, if you want, it becomes the image of, okay, I should rather put rho lambda than, it's not the chi lambda, it's the rho lambda. I evaluate the representation associated with lambda on gamma. I get some matrix here, and I evaluate it on Gn plus 1 here. And what I claim is that if there is a natural identification of this space with this space, so that these two elements are equal. It is just a computation. You need just to find here, you see Mn plus 1 of C. You can see this as the functions on Sn plus 1 over Sn, on the quotient, on the coset space of Sn plus 1 over Sn. And you can even further identify this space with the transpositions, the identity, and all the transpositions I n plus 1. This you can identify with 1, I n plus 1. It's a set with n plus 1 element. And when you do this identification, it just becomes a very simple computation to do that. Excuse me? From what to what? From? To there. Well, now what I claim is that, yes, you have to evaluate the moments. What I claim is that the moments, this element is in the commutant of the representation Sn. And if I write down the matrix of Jn, if I now try to diagonalize this element, I will get some block matrix, like that. There will be zeros. And there will be an eigenvalue on each of the representations, irreducible representation of Sn appearing here. Because this element here is in the, it is in the commutant of Sn. I'm taking rho lambda and I evaluate it in the rho gn plus 1. Oh, it's an induced representation. It's the induced representation of rho lambda that I need. Yes, sorry, yes. No, here you don't need to induce because you are evaluated on elements in Sn. What I claim, in order you want to construct a representation of Sn plus 1. You have a representation of Sn plus 1 in this space, which I call the induced representation that I introduced last time. So this is the induced representation. Because of that, you can this element can operates in this space. Well, here it's a non-dom. It's a matrix on this space actually, not an element in the space, but a matrix on this space. And what I claim is that the underlying space, that is C to the n plus 1 tensor V lambda, it can be seen as the induced representation from Sn to Sn plus 1. And then, remember what happens when you induce the representation lambda. I make, so here is my, is my diagram. What happens when I induce from Sn to Sn plus 1? Well, I get irreducible components, which are given by one of these things here. What? Hmm? Yes, one is missing. Okay. And on each of these things, on each of these components of the representation Jn plus 1, of Sn plus 1, Jn plus 1 takes a certain, has a certain eigenvalue which is given by the abscissa of these boxes. And the dimension, the corresponding dimension is the dimension of the irreducible representation of Sn plus 1. And in the end, I get the transition measure for the distribution of lambda. It has exactly, the eigenvalues are the support of this measure. And you can check by using as usual, the Hooke formula that the weights are correct. This is what I said last time. Therefore, you have this. Yes. That's it. When you induce, you start from an irreducible representation of Sn, you induce, and you realize it as the sum of irreducible representation of Sn plus 1. Okay. Yes.
So, Rolanda maps permutation to matrices, if we spaces. So Rolanda of gamma is basically a matrix of matrices.
Yeah.
And Rolanda of Jn plus 1 is just a matrix. And the entries are just.
It is a matrix, but in the larger space. So this is a matrix. This is a matrix of matrices, but you can write it also as a matrix in a larger space by taking C to the n plus 1 tensor V lambda. Okay. What I claim is that I claim that the endomorphism of
but Rolanda of Gn plus 1 is a matrix which is n plus 1 times n plus 1.
No. It's a large matrix. Yeah.
Okay, but then the dimension would be lambda.
This is a representation of lambda of Sn. I tensor with Cn plus 1. And I said that the induced representation is a representation on this space. So it's a matrix on this space, and this space is the same thing as this space. And then when you make all this identification, you get this formula, which is here. And, of course, this formula, which is here. Oh, if I take the co-transition measure? If I take the co-transition measure, then instead of Jn plus 1, I should look at Jn, actually. Well, the moments of the co-transition measure are just given by k lambda of the analog of mk are just the powers of Jn. These elements are these things are just the moments of the transition measure, because I said that the co-transition measure, is a distribution of Jn. But here we are not looking at Jn, we are looking at Jn plus 1 in the induced representation, which is something else. No, for the moment, I'm just defining, for the moment, I'm not speaking about asymptotics. Now I'm going to say something about exact results. And this exact result will relate my two multiplicative bases of, or generating sets of elements. Remember, I had three bases, or they are not exactly bases, there are relations between them in general, but there are three generating sets. MK, RK, and sigma k. Of course, if you fix n, they generate a finite dimensional algebra, so there must be a relation between them, polynomial relations.
N of them are independent.
Yes. If you take n large enough, then the relations become more and more involve more larger and larger degree. But for fixed n, they fix it's a finite dimensional algebra, of course. But we have these three sets of elements, and what I say is that there is a relation there exist universal polynomials. Because it is zero. It is zero. I could put it, but it's not very interesting because it takes the value 0, so it's not really. You don't need it. And then, and R2 actually is equal to. And the remarkable fact is that these polynomials are completely general. They don't depend on n. The polynomials don't depend on n. I will give you the first ones. So, is it R3? So, sorry. So the first one is this one. But what is this? This is just n. But then we have, if you evaluate it in some group, but the relation is always true. I don't know them by heart, but then Sorry, I'm missing. This is sigma 3. I just write a few of them. So here are the few of the polynomials. These polynomials just express relations between two sets in the group algebra, two elements, two family of elements in the group algebra of the symmetric group, in the center of the group algebra of the symmetric group, for any symmetric group. They are valid for any symmetric group, and they are completely universal. You can see them. And, well, first thing I would say, if you can put a degree on the variables by saying that the degree of Rk is k. Then the term of highest degree is just a monomial, degree 1 monomial. And this is just another way of stating the asymptotic result that I said about the characters of the symmetric group. When the size of the group goes to infinity, the Rk's grow, I mean, on some lambda, when you evaluate them using these formulas, they become the characters, the free cumulants of lambda. And you can see that actually the relations that I gave, the asymptotic relations that I gave, if you just evaluate it for one cycle, in which case there is only one term in the formula, that is, remember, chi lambda of some cycle, ck, cycle of length k, of order k, then this is times, I think it's n to the minus k minus 1 over 2 in this case, plus smaller terms. This is the asymptotic. And this relation, now we see that this relation is just the fact that we have an exact polynomial relation. And in this polynomial relation, the first term is just this term. And it has the highest degree when you put the degree on the variable according to this formula. It is the highest degree.
Something related to the fact that you could have defined some sigma theta, like a sum over I, which are not distinct.
Well, what does it mean to have a cyclic permutation on elements which are not distinct? You have to.
Well, somehow you are taking a cycle, but when it's with repeated things, you cut into smaller cycles, and that makes those power.
Okay.
Is it that, or it's a different?
How do you prove that? One way of proving this is just to do the computation, to use these, the formula which are, to use the formula which expresses the moments, mk, in terms of conjugacy classes. You see, you can expand mk into conjugacy classes of symmetric groups.
Okay. The trace.
Yeah. Yes, and then by you can because this. You can expand this is a trace. I recall this is essentially the trace of gamma to the n, to the k. You can, of course, expand this as a sum of product of transpositions. And now you have to see that from this sum, there is the computation that you do actually don't involve the n that you are. They involve the n, but the n is hidden here, actually. I said the formula don't depend on n, but the n is hidden here, of course. There's a trick. But you see the formula is very beautiful because when you put R2 instead of n, the formula must become much more nicer than if I had replaced R2 everywhere by n, it would be a bit ugly. But here they are much nicer. So the proof of that is just by you just expand this and you manipulate your things and you expand into it gives you a way of computing these coefficients here, but it's not very good. It's very low to do that. It's very so you can prove that this coefficient exists, that they are integers, actually. They exist, they are integers. But if you want to do that, then you have to, as I said, you have to expand conjugacy classes into products of cycles, which is a very difficult thing to do. You know that there exists some number of decompositions. There are some integers, but you don't know how to compute them in general. It's very difficult. You can do that using character theory, but this is what we are doing here, more or less. But this is complicated. But and when you do that, you can. I computed them quite a little bit farther, and you make you notice something here. What do you notice about the coefficient, apart from the fact that they are integers? They seem to be non-negative. Up to now, they are not. Well, I continued up to 11, and I checked that they are all non-negative. And actually, Kerhoff did say this computation also, and he gave a talk in which he conjectured that these are all non-negative. And this is, but I mean, from this expansion, from this way of writing the expansion, it is not at all obvious that it is true. It is a very difficult problem, actually. And I'm going now to, well, this problem has been solved. I will not give you the solution. I will give you just some idea. But before that, I want to show you another way of computing, defining these polynomials, which has absolutely nothing to do with a symmetry group, or a priori nothing to do. It is a very simple thing. Let me introduce a generating function, h of z, which is z minus the sum of bj, z to the 1 minus j. I guess I should start from 2, probably, yes. Bj are some variables.
J greater or equal to 2.
What? Well, I think, I'm not sure. I should check. I should check because I'm always confused by the fact that there is this R1 which is equal to 0. So I just, yes, use some. It's just a generic generating series, say. Yes, you have to start from 2. That's right. Because it's always related to the fact that, so here I start with 2. Or if you want, B1 is equal to 0. And now let me define this. The coefficient of z minus 1 in the case power of h. What do you recognize here for people who are? This is the Lagrange inversion formula. So yes, but I mean, essentially it's a Lagrange inversion formula. You have to play with it. It's nice to write it in this way. I could use 1 over z instead, but in this way it's nice to write it down. It is essentially the Lagrange inversion formula. It states that there is some relation between the generating series for h and the generating series for r.
Sorry?
Yes?
Bj are defined to respect these two equations.
This defines, the bj's are just variables, arbitrary variables. It's, if you want, I'm talking about the polynomial algebra in the bj's. And these elements belong to the polynomial algebra in the bj's. There are polynomials in the bj's. And the first term is just, I think it should be bk. They can be written as bk plus smaller.
Before we had that case where numbers, then we switched to our case are coefficients, and now they are polynomials.
Yeah. What I claim is that rk plus 1 is bk plus polynomials in the bj's, j smaller than k minus 1. This is no. Yes, maybe. Yes, you're right. Probably, yes. And now, let me write sigma k, another set of polynomials in the bj's, it is given by minus 1 over k, z minus 1. The coefficient of z minus 1 is h of z minus 1, etc., h of z minus k plus 1. You see, this is just a small perturbation of the preceding formula. As you see, we are replacing h of z to the k by a product of shifted z. And we are evaluating around z around the infinity, you see, because we are taking the residue. Therefore, it is just a small perturbation.
This is apparently no motivation at all.
What?
This is apparently motivated.
Yes, and my claim is that the relation between sigma k, of course there will be a relation between sigma k and rk plus 1. All these polynomial relations you can invert because they are a triangular system. And the claim is that the polynomials are here. They are the same polynomials. Yes?
I'm confused. So far, rk plus 1 that are written on this blackboard are different from rk. So can you put... What I
claim is that if you choose the bj's as familiar variables, all these things are just polynomials in the bj's. These things are polynomials in the bj's. And the polynomial formula are inverted. You can express the bj's in terms of the sigmas or the rk's. Mm-hmm.
You have to expand.
You have to expand. You have to expand this.
It's just elimination, right?
Yeah.
Rk's and bk's are both functions of b.
Yes. Yes. No, but because you see you have negative powers, so you can expand. There is no problem of convergence here.
You have to expand as if z is larger than k.
Where do you expand around 0?
No, I'm not expanding around 0. I'm taking the... You see these are negative powers here. It's a power... This is a power series in the bj's. This is a power series in the bj's. It's 1 over z, yes. It's expanded in 1 over z. It's, if you want, that's the usual expansion of 1 over z around infinity, yes?
Is there any way in which one can think of moments in factorial?
You can think of this as if you want, yes.
It looks like...
Why? So, this is an amazing formula. And because, you see, you don't need symmetric groups to define these polynomials. They are just defined by this very elementary way. You just have you have just a generating series, and then you do the Lagrange inversion, and you do the perturbed Lagrange inversion. Yes?
Just to continue on this remark, usually the relation between the two are Stirling numbers, right? So are these guys something
well, it's when you expand, but here you expand the inverse, so I don't see if you will get Stirling numbers here. You will get the inverse series of series numbers. Yeah. 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 Certainly, Stirling numbers are not very far from here, but What? I don't know. I don't know. This is up to you to find some. And maybe a Q version, I don't know. Yes, no, but in this. You know a Q version of this formula? Yeah, I know there are Q versions of the Lagrange inversion formula, but I don't think when Q goes to 1, you get this one. You don't get that. So, is there a Q version of this formula? I mean, certainly there is a Q version of this formula. So that is a Q inversion formula, like Q Lagrange, but this I don't know. It's something that would be interesting also to. What? Yeah, yeah. Well, this is there is some you see there is some connection between the generating series of sigma and h, but I don't know exactly what it means. I mean, if you compose the two, you get something which is almost z, but you have some other terms. It's a perturbation of Lagrange inversion. So if you compose the two series, you will get z plus, in some sense, small terms, whatever small means. Yes?
Is it in general true that the sum of the coefficients of the linear terms is the factorial?
Okay. Let me finish. Nice observation. I should know that. Okay, I have other values. Probably yes. Probably there must be some. Oh, you mean? You mean linear terms? The terms. Oh yes, yes. I will give you the explanation now. But you see, it is quite amazing. But now, how do you prove that these polynomials are the same? So and actually this is a consequence of the Frobenius formula for characters. What is Frobenius formula for characters? It is, well, let me take a partition lambda, and let me put phi of z is equal to the product z minus lambda I minus n plus I. Then Frobenius formula tells you that you take this following factorial of n, multiply by the character of a cycle of order k, which is essentially, this is essentially what I had in my, this is essentially sigma k, you see, because if you remember, up to a factor k, this is sigma k. Then this is minus 1 over k, the coefficient of z minus 1 in z minus 1, z minus k plus 1, times phi of z minus k over phi of z. It's n and minus 1 and minus 2. Pick one element and the second element and the third, etc. I had a sum of I1, Ik, etc. This is this number. So this is a formula which is an old formula, going back to Frobenius. And using this formula, you can derive the fact that the polynomials are the same here, which is because there is a way to relate this. Okay, I give you the formula, and then it's a little exercise. Z phi of z minus 1 over phi of z is equal to 1 over g lambda of z plus n minus 1. This is the formula. And J lambda it was the Stiegis transform of the transition measure. Remember this formula that I wrote, the quotient of the polynomials with roots the x and the y's.
This was not the Frobenius, not even
What? This formula? Well, this formula is, once you know it is true, it is easy to check. And actually, this way of computing the Kerhoff polynomial, it was shown to me by Okunkov. He found that, he showed me that actually, I didn't know how to compute these polynomials, and then he showed me that you could compute them by using these formulas. I mean, this is very easy to implement. I implemented this in Maple, and I got them. The computation using the permutation are horrible. They tell you that you have, but of course, neither of these description of the curve polynomial accounts for the fact that the coefficients seem to be positive integers, non-negative integers. This is a mystery. Here, why are there non-negative integer here? It's a big mystery. I mean, but as Philippe mentioned, if you take the linear terms, then you get. If you take the sum of the linear terms, you get something like. Yes, you get 6, 2, 1, 24. The sum of the coefficients of the linear terms. And actually, what you can prove, it is not too difficult to prove, but it requires just a few computations, is that the coefficients of are, let me write it correctly because I don't want to make a mistake. Yes, the coefficient of R k plus 1 minus 2L. As you see, there is some parity conditions, as you can see, which is not difficult to see because of parity of the transposition. It's not difficult to see that you have some parity on the degree. All the if in the expansion of sigma k you have only terms which have the opposite degree, the opposite parity as the parity of k. So the coefficient of this element in the expansion of sigma k is equal to the number of cycles C of order k in Sk such that 1, 2, k times C has k minus 2L cycles. These are these numbers. And of course, the sum of them has to be k factorial, as you see, because you're just counting. You just take your favorite cycle, you multiply it by another cycle of the full cycle, and you count how many cycles are in the decomposition. And this gives you these numbers, which are here. So in some sense, they count the number of factorization of this cycle here into another cycle of length k, of order k, and another permutation which has exactly k minus 2L cycles.
So this is somewhat written in the table of graphs because you are composing.
Number of cycles, the total number of cycles is k minus 1.
It's a number of such permutations. C. It's not the number of the cycles of the permutation. You take a permutation of, if you want, it is a number of factorization. 1, 2, k is equal to C times sigma, where C is a cycle of order k.
Yes, but there is in fact a sheet, sigma
Hmm?
pi.
You should have said k factorial, but k minus 1 factorial.
Yes. It's yes. Up to yeah. Yeah. It's yeah. So you have this interpretation of the coefficients of the Kerhoff polynomials, the linear terms, and actually this is not too difficult to prove using what we know about the Jershis-Murphy element, because you know the generating function for the Cauchy-Murphy elements is just this number of cycles which are here. Remember that I wrote that the product of 1 plus z gi is equal to the sum of z to the length of sigma. There is a deep connection between the Cauchy-Murphy element and the length of the permutations. The generating function of the permutation according to the length can be factored into product of Cauchy-Murphy element, as I said in the. And well, using that, I mean, it's you can prove these things. But we know now that the coefficients are actually non-negative integers. It was proved by Valentin Ferret in his PhD in 2009. And then a few years later, with Maciej Dolega and Piotr Szniady, they gave an interpretation in terms of factorization in the symmetry groups, which is very close to, which is a generalization in some sense of these remarks for the elements of degree 1. And I think it's in a paper in Advances in Math around 2011 or 12 or something like that. So they have. They found a very nice, but it's too complicated. And I will not be able to talk about it. It's a bit more complicated. What? Oh, that's what I say. They have an interpretation for all the terms. All the terms. No, the linear terms. I give you this interpretation. This is something I did some years ago. But what? It's a number of factorization. You count center exactly like that. You count factorization in the symmetry group, which have some form, depending on the terms that you want to look at. That's what they found.
So it's like factorization into more permutations?
Yeah, it's more complicated. Okay, I don't want to go into that. I would not be able to explain now. So I would have to look it up because I mean it's not simple. I mean it's really very tricky. I mean really, and for that they had to really understand many things about characters, which are highly non-trivial. It's certainly not something easy, but it's very beautiful because you see this from these expressions. You see it has nothing to do a priori with symmetric groups. You just have two series and you just make a small deformation of the Lagrange inversion formula, and you get these positive coefficients. And miraculously, they turn out to be related to symmetry groups and to have some combinatorial meaning. And this is nice. What time is it now? Maybe it's time to make a little break. 2 minutes. 3 minutes. Sur Internet, ça a été filmé. Et après, je suis en train d'écrire des notes, mais ça ne sera pas fini tout de suite, mais je peux vous les envoyer. Vous êtes étudiant à... Non, pas du tout. D'accord. Non, parce que je me demande s'il y a des étudiants qui veulent passer l'examen, parce que c'est censé être un cours M2, mais j'ai peur que ça soit un peu difficile. Pas complètement, mais un peu. Hein? Oui, oui, parce que je vais plus l'utiliser, les polyèmes de Karoff. Là. Non, je vais parler de l'asymptotique maintenant. Je vais revenir sur l'asymptotique. C'était une petite parenthèse combinatoire.
Donc la base des cycles, mais avec les index répétés, elle n'est pas bonne.
Les cycles avec les index répétés.
Si dans ta formule de sigma k,
Oui.
tu admettais que les i...
Oui, mais je dois définir qu'est-ce que c'est qu'un cycle avec des indices répétés, je ne sais pas ce que c'est. Ou alors c'est un produit de cycle, quand tu en répètes le 1 pour la première fois, je ne sais pas ce que ça veut dire. Mais...
La base, tu prends ta matrice gamme, tu enlèves les zéros,
ouais.
c'est-à-dire les lignes...
La première ligne et première colonne,
la
oui.
ligne 0, et tu fais que les produits de la binaire à la puissance k et la
Oui.
trace.
Oui, c'est ce qu'il faut faire, oui. Oui.
Ceci, c'est aussi des termes dominantes includées.
Oui.
Et puis, il y a d'autres choses.
Oui, bien sûr. Non, mais c'est comme ça que tu démontres qu'il existe des coefficients, que ça se développe. Tu peux même démontrer qu'ils sont entiers. Enfin, tu peux faire ça, mais oui, c'est comme ça que j'avais fait pour montrer que ces polynômes existent. Mais...
A priori, c'est autre base. C'est une autre base. A priori, c'est une base différente.
Oui. Oui. Mais bon, celles-là, c'est les plus intéressantes. Les cumulants libres et puis les cycles, c'est deux bases très naturelles. Les cumulants libres, c'est pas évident que c'est une base naturelle, a priori, mais bon, il se trouve que ça a des propriétés remarquables. Si tu essayes pas de faire l'asymptotique des caractères, tu vas jamais trouver les cumulants libres. Parce qu'a priori, il n'y a aucune raison. Enfin, s'il y a la formule de Frobenius, il faut deviner que à cause de la formule de Frobenius, ces coefficients de l'inverse où tu remplaces z, z-1, etc., juste par z à la puissance k, ça, bon, c'est un peu... Well, let us go back to work. Now I will come back to the asymptotic of representations. And for this, I will use the same tool that I used in the case of the limit in the theory of Kerr-Ferschik, the theory of S infinity. I will use two facts. First, that for my characters, in the limits that I am interested in, that is in the limit where my characters have some bounds like that, on the size of the partition. The length of the rows and columns are of the order square root of n. Then I know by my asymptotic formula that I have such a bound. And the second thing that I know is that chi lambda of sigma 1, sigma 2 is, say, if I take the difference, so for two permutations whose support are disjoint, and these estimations are valid for such diagrams. and for, say, if we have a bound on the length, say, on the length of sigma. If we put some bound on the length of the permutations, then we can even find uniform estimates. Now that we know the Kerov polynomials, we can even give quite precise estimates here, because we have we know the first term is given by the first term will dominate, and then we can bound the other terms. At least if we know how to bound the coefficients of the Kerov polynomial, we have very good bounds for the remainder terms. Therefore, we have, when we have irreducible characters, we have two things. We have, on the one hand, they decay at some speed, which is the speed is the half of the length of the permutation. And we know that they factorize up to some order. Of course, the order of magnitude of this thing here should be the length of lambda, the size of lambda to the minus the size of sigma 1, sigma 2 over 2. And here we know that we can divide by another power, and it will be so it will be smaller. And now I will introduce a class of characters, not irreducible characters, but what I call characters are positive type functions, which are normalized. So psi will be positive type normalized, and central. That is, I know that such a psi will always be written where as a convex combination of characters. So the lambda, the p lambda have some 1, and they are non-negative real numbers. Therefore, if I have such functions, to give such a function is exactly equivalent to give a probability measure on the set of partitions. It's the same thing. So my class of characters will be indexed by, let me take a sequence of constants, CL, non-negative constant, and I will say that sorry. I will say that my character belongs to my class, indexed by C, if it satisfies the following bounds. It's a modulus. So it is bounded by some constant times the n to the minus the length of the permutation over 2. And I say this will be true for L equal 2, 3, L. Suppose I have some, so I look at the class of characters which satisfy this kind of bounds. And now I will state a theorem. So remember that such a function here is equivalent to a probability measure on the set of partitions. So my claim is that there exists a constant k. K will depend on the sequence C, such that if psi of sigma 1, sigma 2 minus psi of sigma 1, psi of sigma 2 smaller than delta n to the minus over 2 for all again, same condition, sigma 1, sigma 2, with the support of sigma 1 and the support of sigma 2 disjoint. And delta is some number. Assume that this is true. Then suppose I have a character which satisfies these bounds. Then what I claim is that the probability, there is a probability here, which is the probability associated with the character, the p lambda, which is here. Well, I claim that the probability that psi of sigma minus chi lambda of sigma smaller than k delta plus 1 over n to the power 1/4, okay, is larger than 1 minus delta plus 1 over n to the 1/2. Well, what does this mean? This means that, and this is true for permutation with length smaller than L.
And again, lambda is something random sampled according to that.
Yes. So here the probability is for lambda here. Lambda is, this means that you are looking at you have the set of partitions here. Lambda, all the partition of n. It's a set of partitions. What I claim is that there is some subset here, some subset of the partitions, which contains almost all the mass. Here, delta is arbitrary, and when n goes to infinity, this can be made very small by taking delta small and n large. And what we see is that here, the difference between these two things should be of the order n to the minus length of sigma over 2, but here we have a small number, which is here.
K depends on that.
K is a constant. I say there exists K. Once K has been chosen, you can let delta go to 0 in this theorem and let n go to infinity and make this as small as you want.
Okay, but it's not, it's written. So K depends on psi, for example.
No. K does not depend on psi. If psi, I say if psi, this is some statement about all psi which satisfy this condition. If psi satisfies this condition, then the associated measure is concentrated on a small subset.
From the statement, it's not clear what K depends.
K depends on the sequence of CL. Sorry, yes, maybe if C and C belongs to the class depending on C. That's the class of. I look at all the positive type function which decay at this speed.
What is C?
Some constant, some real numbers, positive real numbers. Some they have to be positive because if it.
There is a psi in the class of C.
Yes, this means that this is true. This means that psi decays. Or psi, if you want, psi is small.
But the K does not depend on the delta.
No, of course it doesn't depend on delta. If it depended on delta, then I would be very bad here.
What is the quantification of delta?
Okay, I say for NA psi in the class C such that this holds, then I have this. Of course, this is interesting only if delta is small, this statement. It is true if delta is whatever you want, but it is only interesting if delta is a small number.
So delta can depend on psi.
For any delta.
I say if psi satisfies this bound, then the measure is concentrated in this sense. And of course, the better the bound satisfied by psi, the better the concentration is. And the bound that is satisfied by psi is exactly controlled by delta.
From your notation, it seems C of C depends on the variable C, which I don't understand.
This variable C here.
So C is the sequence of CL.
Yes, C1 up to CL.
Okay, that was.
Yes, psi is almost multiplicative. This is what it says. Yes, the psi. I say if, of course, if psi corresponds to a probability measure which is concentrated on a very small set, because the chi lambda are multiplicative, psi will be multiplicative. Okay, in the neighborhood of some lambda. For some topology on lambda, the topology, for example, given by the values of the characters on small permutations. I say if, of course, if it is concentrated on some small set, in this sense, psi, the probability associated with psi will be almost equal to one of the characters which are here, which will be very close. And therefore, it will be almost multiplicative because all of them are almost multiplicative. And they are almost all of them take the same value on small permutations or very close values. So in one sense, there is an obvious statement that if psi, the measure associated with psi is concentrated, then psi is almost multiplicative. And the statement, of course, is the converse. If psi is almost multiplicative, then it has to be concentrated around a very small part of the set of partitions. Of course, this has only meaning when n is very large, because for n 5 equal 5, it doesn't mean anything. This is
every 2 points which are distant in topology, there exists a sigma of support which distinguishes them.
Yes, yes. Well, of course, if you take two characters and they are equal on all sigmas, they are equal by definition. Yeah, so this function, the evaluation of permutation, is certainly distinguishes your characters. And if you know enough of, if you know just a few of permutation, you can distinguish them in some sense. But the more you know, the bigger L is, of course, the smaller the set will be here. Yes, I stated a theorem as that kind, but it was with there was nothing like that. It was in the Thoma simplex. It was in the Thoma simplex, and it was in the case where psi, and then the bound here was trivial. There was no bound here, because all characters are between 0 and 1. They are normalized characters, so there was no bound. And I claim exactly the same thing essentially. That if you have asymptotic factorization, if your character is almost factorized, then it is almost an irreducible character. In some sense, the factorization is a characterization of the irreducibility of the characters, in some asymptotic sense. And it was true for characters of S infinity, but that we know by the theory of characters of S infinity that they have to factorize. But what we see here is that it holds true also in this sense, in the asymptotic sense, which is much finer than because we have to take into account the length of the permutation. It's really the decay rate of the characters which is involved here. You see that the factorization involves in a very essential way the decay rate of the characters. Yes, this is what is really interesting to see that this thing which was in some sense, I don't say obvious, but which was very natural in the case of the Thoma, in the Kerr-Verschick theory, that the characters should asymptotically factorize because they approach. Well, we know for characters of S infinity that factorization is equivalent to extremality. But here we see there is a very analogous statement. And the proof of the statement, once I explain, it's essentially the same idea, but you have to, you have again to use you have to use again these gamma matrices. So how do you use them? Well, I hope I get my. I put my. Yes.
on the scale n, and now
Yes.
you are on the scale square root of n.
Exactly, exactly. And you have to take into account the decay rate of the characters in order to do that. Well, you know, psi, what I say is that psi of, I should find my, I lost my, no, it's here. Okay, yes. How do you prove that? Well, what you have to do is you will evaluate the following thing. Psi of so the mk will be the same m that I had, which are elements in the group algebra, which are the moments of the gamma matrix. Now I can evaluate a character on such an element. And I divide them by n to the k1 over 2.
That's good because they are multiplicative pairs.
Yes. And I want to evaluate the difference between the main problem is to evaluate this difference, which is here. And so why is it, why do you have to do that? Well, it's very simple. This is just the sum over lambda of pi lambda. And now, if I look in the irreducible representation corresponding to lambda, these are just the moments of the matrix. So these are just x to the k1 d mu of lambda. So it's lambda scaled by a factor square root of n. Because I have divided by a to the power k1 over 2. This is equal to this, and this is just the sum of pi lambda, so integral of x to the k1 d mu lambda over square root of n of x, and you take the product of these things. I'm just looking at the, if you want, the covariance. It's just the covariance. What I prove, I want to prove that these random variables, mk over n to the kr over 2, these random variables are concentrated around their mean. I know what is their mean. Their mean are the value of the character. Their mean are these things here. This is the mean value, so sum of lambda of this. And I want to prove that these things are concentrated around their mean value. So what I prove is that the expectation factorize. What? And I should write here. Here, this is the sum of a lambda of pi lambda integral of x k r d mu.
So again, the theorem is telling that the topology of the characters is the topology of mu with respect to.
Yes. What this? If I prove that this is small, then this means that the say compared to the this value here is the expected value with respect to the measure p lambda of the case moment of my measure. And now I want to prove that this expected value, okay, it is something, and I want to prove now that the variance of this random variable, which is this you see it is a random variable because lambda is random, and we are taking the integral with respect to the measure p lambda. I want to prove that this variance is small. And so for this, I need to, well, I could just do that with r equal 2 and k1 equal k2, actually. It's enough. But I mean, it's exactly the same thing to prove that expectation factorizes more generally. I mean, it's essentially the same proof. We'll give you the thing. And now, what do you do in order to do that? Well, you expand this term on the left, psi. So this is psi of the sum. In order to get mk1, for example, you have to take all products like that. And then you will look at ak2, say it's y1. I will have a first bunch of y's, then a second corresponding to m2, say a1, 2, and so on. I can go on like that. And I will have a sum over all possible indices in this sum. And I have already tried to estimate, and I need to estimate such things. I have already explained last time how to do that. You need to understand what is the partition formed by the sequence of indices. And then some partition disappear in the limit because you can evaluate them. In order to evaluate them, you need you need to have a bound because you are evaluated psi. What you just need is you just need to have a bound on the values of the characters, and you need to have a bound on the value of the difference between. You need to have an almost multiplicativity. And then what we see is that essentially this large sum will reduce, it will be a sum of all partitions induced by the sequences of indices. And what I said last time is that we can reduce this to non-crossing partitions. All the partitions which are not non-crossing will give 0 contribution in the end. So this means, and here we have I1 is equal to I1 here. So we will have a partition where this is equal to this is equal to this, and so on. You see, these are the terms corresponding to the I with an index 1, an index 2, an index 3, etc. And what we see is that when we are summing over all partitions so that this is disjoint from this because the partition has to be non-crossing. And this is disjoint from this, disjoint from this, disjoint from this. And then, in the end, the sum will factorize into products of terms exactly like this. It is just the same argument as I used last time. But for this, we have to really analyze using the decay rates of the characters and the asymptotic multiplicativity. If we use these properties of the characters that we have assumed, then we can estimate the difference between these two expressions and see that it is small in the scale that we are looking at. This is the idea. I will not give you the details. I mean, it's quite awful if you try to write down all the details. I did it some years ago, but it's,
so the crossing between different blocks will make the same decay that it would if it were within the block?
It will make a worse decay. If you have some crossing like that, what I say is that when every partition which has a crossing, and of course inside all this you will have only non-crossing partition which will appear. But this I don't really care because. But the claim is that each time I have a crossing like that, two partition where there is some crossing like that, then the decay rate of the corresponding element in the sum is smaller than the whole sum, the typical element in a non-crossing partition. For a non-crossing partition, you can estimate, and you see exactly, you have an estimate. which is the order that you want. And for the other ones, the decay is worse. Oh, not worse, it's better, I would say. it decays more. Because you have to count how many such, you have to count how many elements you have and the length of the permutation. It's a very delicate balancing between the two. It's very delicate. I mean, it's much more delicate than what we had in the case of the Kerr-Fershik, because then you really have to take into account the length of the partition, because the decay of psi depends on the length of the partition. So it is quite delicate to do the asymptotic analysis. I will not try to do it now because it's quite a mess. But yes? Yeah. What? Yes, multiplicatively. Yeah. Yes, certainly.
I'm missing the basic fact of why is it enough.
Oh yes, because then you can, of course, then you can evaluate. If you know how to evaluate the moments, you can evaluate also the cumulants, the free cumulants. And if you know the free cumulants, you know the value of the characters. Yeah, of small elements which are of length smaller than L. There are formulas for going from moments to free cumulants and from free cumulants to characters. And since all the size of the elements are bounded, you get some constant k, which is okay. Some constant you have to compute, but certainly in the end you will get this, and you will get this just by the Markov inequality. Of course, you just compute the variance, and then you deduce the probability of being away from your expectation by just using Markov inequality, which is the 1/4 which you get here. It is just a Markov inequality, of course. Once you have a bound on the variance. So the idea is just you compute a bound on the variance using this combinatorics, which is here. And once you have the bound on the variance, you know that the value of psi, the value of the moments of the value of psi on the mk is equal to the value, is very close to the value of one of the chi lambda. And if it is true for the value on the mk, it will be also true for the values on the free cumulants. And if it's true on the free cumulants, it will be true also on the when you evaluate on the cycles. But so all these things are equivalent. You can pass from one to the other just by polynomial with a finite size formulas. It's equivalent to know that the moments are close, or to know that the values of the characters are close, or to know that the values of the free cumulants are close between psi and chi lambda. It's enough. And so in the end, you get this, which is just apply Markov inequality to your evaluation of the variance. That's all. You have computed the variance of this. This is the mean value. And this is a random variable where lambda is random, and you have computed the variance of this random variable, so you know that you know its expectation and you know its variance, so you have a bound on the tail probability. That's all. Well, now I will give some application of this to some. I don't know how much time I have. Okay, I have a few minutes, and I can explain what is how to apply this to operations on the representation of symmetric groups. My first example will be an example I will give the restriction. If you remember, it was the experiment that I made yesterday at the beginning. I had a big representation of a big group, and I restricted to a subgroup of size half. And we saw that there was some curve going on. So I will take Sn, lambda partition of n, and I will assume that there is some bound on there is some bound on the character, on the partition associated with the representation. And now I restrict Sn to S, say SP1 times SP2 times SPR, where each Pi, say, is equal to TIN, and TI, of course, is between 0 and 1, and the sum of TI, so TI positive, and the sum of TI is smaller than 1. I restrict to a subgroup, to a product of symmetric groups. And I want to understand how this representation restricts to such a product of groups. Well, we know, well, we can apply the previous results because we know that since chi lambda is an irreducible character of lambda very large, and lambda has these bounds, we know that chi lambda is almost multiplicative. That is chi lambda of sigma 1, sigma 2, minus chi lambda of sigma 1, chi lambda of sigma 2. This is small, it will satisfy some bound. So I can apply the previous result to the restriction of chi lambda to my subgroup SP1, for example. And what I get is that, the values of chi lambda if I reduce it on SP1, on the small group SP1, well, the values will be concentrated around the values of some irreducible characters. And what happens when I do the scaling? Now you have to be careful because there is some scaling between assume that my that my partition is lambda here. It's lambda. If I don't make any scaling, the area which is here will be n. Now, what I claim is that what I claim is that the operation corresponding to the restriction corresponds to free compression. That is, if I have my character, of course, the restriction of the character chi lambda to Sn to SP1, say, to SP is equal to the value of the character on Sn, but remember that I had this, there is a difference in the sense that R2 is equal to n. This is the only one which is different in the two. Which is, this R2 is not given by the value of the character on some conjugacy class. It is a free cumulant. All the other ones, they are given by evaluation of the character. What? No, because when you evaluate it, it is equal to 1, the normalized character. So the only difference between, this means that chi lambda, if I associate to lambda a measure, mu lambda, then I know that the free cumulants of lambda will be the free cumulants of the measure by definition. And now, when I do the restriction, I see that the free cumulants of, say, lambda prime, the typical representation in SP, so it will be a partition of P. A partition of P is the typical representation that we'll get when I do the restriction. And what I claim is that its free cumulants will be P, and then R3 of lambda, etc.
What do you mean by typical?
what I claim is that I know that this is almost factorized. This means that when I do the restriction, it will again be almost factorized, and it will satisfy the bound that I had in my previous theorem. Therefore, I know that when I decompose it on the SP, it will be supported on a very small set. And this small set is exactly the value, the set of characters which have the same values as my psi. You know, here this becomes psi. When I do the restriction to SP, say for example. When I restrict it to SP, it is a character, and I can decompose it in a reducible representation of SP. And now, of course, the values of the characters, of the normalized character, will be the same, because it is just the restriction. But there is one free cumulant which will not be the same. It is a second cumulant. Now, I could also divide everything by square root of modulus of lambda, if you want. Here. I could divide everything by square root of n, say. And then this means that if I do that, I divide this by n to the 3/2 and so on. And then this and then here I get say t. When I do the scaling. Yeah, assuming that p is equal to t times n. T is some number between 0 and 1. And this means that, there exists, what I claim is that there exists a unique curve, which I call, say, let me call omega this curve. That is the curve of lambda divided by square root of n. It is some curve. The size, the surface below omega will be equal to 1. And I claim there is a unique curve, omega t, which is here, and whose sequence of free cumulants will be given by the following. It has the same free cumulants as omega, except for t, which is here.
Did you get that all the bigger cumulants would be constant?
What do you mean? Yes.
I mean you said
yes. Okay. Yes. Sorry. No. I think yes. Yes. Yeah. Because I should divide by t. So there is some t to the. There is t square here, t3, etc. So it is exactly the operation that I described before, and it consists in the following: you take a free random variable, and you take pi x pi, where pi is a projection. And the trace of pi, the normalized trace of pi, is equal to t between 0 and 1. When you do this projection here, you get some new. If you start with a probability measure, which is a distribution of mu, mu will be free with the projection. I am in some non-commutative probability space. X is free with the projection. And I looked at pxp. And if you remember, it was a random matrix model that I showed you at the beginning of the preceding lecture. I had some x here, which was also a projection, actually, in this case. And I sandwich x between two projections. That is, I extract a certain corner of the matrix of x. And I look at the values of the eigenvalues, which are random, but which turn out to be almost deterministic in the large n limit. And this is exactly what I do here. And actually, if you do the computation for the square here, and you normalize the square, say, in order to have -1 and 1 here, and then you see that if you take t equal to 1/2, you get the arc sign distribution. And what I claim is that the arc sign distribution is the transition measure corresponding to the curve omega, which is here, which was the picture that we had in the previous lecture. If you remember, if I do When I do the restriction, I obtain a triangle in the end. But of course, in principle, you could compute for any starting, you take any shape omega, which corresponds to Lipschitz function. You compute its free cumulants, you apply this operation, and you get a new shape omega t, and this shape omega t gives you exactly what you get when you apply, when you do this, when you perform this random shrinking, yes, of the diagram by erasing the, you erase according to the co-transition measure, you erase the squares until you have erased a proportion, and that it remains only a proportion of t, and you find some shape omega, which is given by. No, there will be no interaction. You will get a restriction to a product of almost irreducible representation in some sense. The restriction will be concentrated. Yeah, yes, you will. They will all be given by shapes which depend only on t and not on the other p's.
Is there a meaning for this restriction?
Oh. Well, no, you just get R copies of several shapes corresponding to the different t's. That's all. That's all you get. Each of them it doesn't see the others. It just concentrates on itself and on its limit shape, and that's all. It doesn't see the others.
Then for the square example, out of the equivalence, can you compute the curve when t is not 1?
Oh yes, of course, yes. In this example, yes, you just multiply the free cumulant. It's a second-degree equation. You can solve it. It's easy. I mean, you see in the beginning it was something like that, if you remember in the picture. And there will be two points here with two masses at -1 and +1, which remain because you are intersecting with a small set with a projection on a set of small dimensions, so it will remain. The two ones which are here will remain. And well, you have to use. Oh, you have to use the formula for the. There is a formula. The formula. I gave the formula. You compute the. Once you have the. You take the logarithm of the. If you remember, I had this formula, which is g mu of z is 1 over z exponential of integral sigma prime of u over, I think it was u minus z du. It's a formula which relates the Stieltjes transform of the measure with the derivative of omega. So sigma is related to omega by sigma of u is just omega of u minus modulus of u over 2. It's just what you get above this wedge. So in principle, you can compute. I mean, of course, in general, it's difficult to compute, but in simple cases like with square roots and things, you can compute that. Certainly, you can compute the formula.
So this is not, does this answer or not to the following question? I take nu,
Yes.
which is a big representation of size n, and I ask, which is the distribution of a phase lambda mu of size Pn 1 minus Pn,
Yeah.
weighted by the little Richardson polynomial.
I explain that now. This is my next example. The next example is I have done restriction. I can do induction now. Induction is the opposite, exactly the opposite. I start with a product of groups, SP1, SP2, SPR, and now I induce the representation. So I start with diagrams lambda 1, lambda r, and I induce the representation to Sn. Okay? Now suppose, now I have to make the right scaling. I will represent all these diagrams by curves, omega, such that the surface, so imagine, of course, that pi is ti times n. I will represent each of them as a curve with a surface here which is equal to Ti by using the appropriate scaling. And what I claim is that when I induce from SP1, SPR, and I have a family of curves, like this curve, lambda, say omega I, there is a unique curve, omega. It will be some curve like that, big curve, with here I will have 1. The surface will be equal to 1. And this curve will be completely determined by the small curves, omega I. Not necessarily. Not necessarily. If it is not equal to smaller than 1, if it is 0, for example, you get the Vergy-Kirchhoff curve. That's a particular example. That's one example. But in general, what you get is that, then if the sum, what you get is that, of course, it is better to use, instead of the curves, to use the measures, mu. And what I say is that the measure will be the sum if I call gamma is 1 minus the sum of the Ti. And nu gamma is it's a semicircle distribution. And the semicircle distribution corresponds to, when I make this transition measure, it corresponds to the to a famous curve, which is known as the Kirchhoff-Verschick limit curve. And you see it is obtained by inducing from, if I take all the Ti to be 0, for example, then gamma is equal to 1. And this curve is obtained by inducing the trivial representation. So it is really the limit of the, so inducing the trivial representation means that you are looking at the regular representation of the group. And this curve is given by, okay, I hope I have the formula somewhere here. Well, I have a more general curve. So I don't know if I can. No, I think it's this one. It's 2 over pi u arc sine u over 2 plus square root of 4 minus u squared. So that's for u between minus 2 and 2. And that's the support of the curve after it's here. It's 2 here and minus 2. And the 2 is related to the 2 in the longest increasing subsequence problem by Ulam. That this is more or less the length of the longest increasing subsequence in some permutation by RSK map. Yes, this is the Plancherel measure because we are looking at the regular representation here. The regular representation, it was of course known by Kirchhoff and Verschick that we have this limit shape. And here we see that it is actually a much more general statement that we have curves corresponding to free convolution of measures, which correspond to inducing from smaller subgroup to a larger subgroup. And if there is some missing part, if the sum is the pi, their sum is not n, we have to convolve with a semicircle distribution, which has some regularizing effect. So, and I don't know what time is it time to just. Well, yes, okay. I could go on, but I think. So what was your question? Does this answer more or less your question, or is it? Great. I'm happy to have answered one of your questions. Huh? Yes, of course, Littlewood-Richardson is exactly computing the multiplicities in this process. Like you take a product of Schur functions, and these multiplicities are here. Of course, here we have a kind of deform because we weight the Littlewood-Richardson coefficient with the dimension of the representation of a symmetric group. We put some weights. And if we put with this weight, we see that in the limit, the Littlewood-Richardson rule has a kind of a deterministic limit, which is given by the free convolution, actually. And I wanted to explain that using a representation of GLN and the Schurweil duality, but unfortunately I don't have time, so sorry. Okay, so thank you very much.